All right, and then let me share. Rotate. Okay, so today, I don't want to say we're going to completely throw away the complex analysis and do real analysis, but we're going to kind of review uh, what I would call two-dimensional calculus. Um, and the reason is probably obvious. In the complex plane, it's isomorphic as a vector space to R2. And so if we're going to be doing integration in the complex plane, well, it's useful to just review some of uh, the, the same topic in R2. Okay, so today is a fast and loose review of two-dimensional calculus, and it'll be full of proofs by examples because this is a review. I don't want to, reprove a bunch of results from real analysis. Okay, so let's start with a definition. So a path in the plane from A to B is a continuous function gamma from some interval from A to B to, so R2, and in the future we'll consider C, such that gamma of A equals A and gamma of B equals B. So the path is called simple if gamma of S is not equal to gamma of T when S is not equal to T. Okay. So this is just the condition of injectivity. Right? So we want our path to be injective. It's called closed if it starts and ends at the same points. So gamma of A is equal to gamma of B. So just pictorially, what do we have? Something like this. The arrow is indicating the direction of the path. So it starts at A, ends at B. This one is a simple path. It's injective. It doesn't cross over itself. We could have something like this. It crosses here. This is certainly a path, but it's not simple. And then we could have something like this, which is a simple closed path. Okay, so in the future, we're going to be very concerned with simple closed paths when we talk about Cauchy's integral theorem and formula, residue theorem, and so on. So maybe as a quick look at the future, a little foreshadowing. It'll turn out that in the complex plane, as long as it's as long as your domain is nice enough, when you integrate over a closed path like this, and so things have to be nice enough such that there are no poles. I'll talk about that later. So there are basically no singularities inside of this loop, wherever it is in the complex plane. That integral will be zero, and that'll be Cauchy's integral theorem. And that is generalized by what's called the residue theorem, which tells us that when we do have poles or singularities inside this loop that we're integrating over, well, actually, we can compute that as well. And it's equivalent to 2 pi I times the sum of these things called the residues of the poles. So we reduce the calculation of the integral to the calculation of these things that depend on the poles. Okay, but that'll all come later. For now, I need to actually talk about what a line integral is and so on. All right, so a little note here. If gamma is a path from A to B, and we have another function, phi, from alpha, beta to r, and if this is strictly increasing and continuous from phi of alpha equals A to phi of beta equals B, then gamma of phi of S is also a path. A to B. So this should be clear, right? If phi is increasing on alpha beta and it starts, so the image traces out a path from A to B, well, then when we compose this with gamma, what we get is another path from A to B. Okay, so what's really happening here is we have a reparameterization of gamma. A parameterization. Okay. Some more terminology, which I don't really care for, but it's what's used in Gamelin, so I'll try to stick to it. We call the image. So whoops, that should be an A. So the image of this entire interval under the path function gamma, we call it the trace of the path. Being somebody who deals a lot with quantum information theory, we have this trace operator, right? And so I don't really like this terminology, but yeah, we'll try to stick to the book. We'll also be absolute animals and sometimes use an abusive notation where we refer to the trace. Sometimes refer to the trace as just gamma when the context is clear. And what we really mean is gamma of the interval from A to B. Okay, so with that out of the way, I'll give you another definition. Put everything. So a curve is a piecewise smooth path. So what does that mean? That means we have gamma of t equals x of t, y of t, and x, y are smooth for each piecewise component. So, if we have a path from A to B, we have a path from B to C, we can compose them to get a path from, a piecewise path from A to B and then B to C. It's still a path, yeah. And if we do this, repeatedly, we get this, path with piecewise components. And what we want is that for each of these components, we can write the path as x of t, y of t, two components. And we want those component functions to be smooth. So smoothness is technically too much to assume here. All we're really ever going to need is continuous differentiability. So really, I think it'll always suffice for these guys to be in C1. Whoops, not that C, C1. Okay. So now I can tell you what a line integral is over a curve. So the line integral of this thing, which we're going to call a differential, along the curve gamma is, well, we use this symbol for it. And it's defined to be the limit as delta x goes to 0 of this sum So think usual Riemann integral. Should be a Q. And here we need a delta yj. Okay, so I've left out some details here. So we're discretizing this path in some way, with some coordinates xj, yj, and then we're summing over the values of p at those coordinates, and this delta xj is x j, let's see, +1 minus xj, and delta yj similarly yj +1 minus yj. Okay. So we call this guy the line integral of this differential whenever these limits exist. Okay. So as we let the distance between the points in our discretization get smaller, we get closer to like this continuous version of a sum, which is supposed to be what an integral is. Right? Okay, so when these limits exist, then this thing is defined and it's called the line integral. Okay, if x and y are continuously differentiable, and x of tj equals xj, and y of tj equals yj, so we're parameterizing our coordinates again for a equals t0 less than t1 up to tn equals b. Then by the mean value theorem, so if you don't know what the mean value theorem is, I'm about to basically quote it verbatim. So here's the mean value theorem. There are some tj stars between tj and tj +1 such that x tj +1 minus x tj is x prime tj star tj +1 minus tj. So this is basically, so what does the mean value theorem tell us? Well, it tells us that the slope that you compute between, so if you have, let me draw a picture, maybe. If we draw the secant line between these 2 points, it has slope so this is the curve x of t. And what the mean value theorem tells us is that this slope, for every consecutive pairs of points in our discretization, there's a point between them such that the derivative at that point is equal to the slope of the secant line. So the tangent line at that point has a slope equivalent to the slope of the secant line. Okay, but same thing holds for y, right? And so what we have is that when we plug this in, let me keep this up here so we have the formula. So when we plug this in, what we find is that so this delta xj is this guy down here, and that's equal to x prime of tj star tj plus 1 minus tj, which is what we'll call delta tj. And same thing goes for y. So what we have here is a limit of, well, this is now x prime tj star delta tj. And this is of course x of tj tj like that. And same thing for y over here. And what we find when we take the limits is that, okay, well, now this is going to turn into our differential. And in both of these cases, this thing is just the derivative of x with respect to t evaluated at tj. And so what we're going to get is that this guy is equal to the integral from a to b now, p of x of t, y of t, dx dt dt, plus the integral from a to b, q of x of t, y of t, dy dt dt. What I was trying to say is we recognize now this limit of this sum as this integral. And likewise for this limit over here. So this is just the definition of the Riemann sum version of the integral. Okay, so to evaluate a line integral over a curve gamma, what we do is we parameterize the curve by some parameterization like this. We calculate dx dt, dy dt, and then we just do the usual Riemann integrals over here. Okay. So it's maybe worth doing a quick example, and I'm going to reuse this example in the future as in this lecture. So let's compute this integral where gamma is the quarter circle from 1, 0 to 0, 1. So that's this quarter circle here. Well, we can absolutely parameterize this in the following way. So all we need to do is remember a little trig. Right, this is the unit circle, right? We can parameterize the unit circle with the cosine and the sine. where theta is between 0 and pi over 2. Okay, so that tells us that the integral over gamma xy dx is the integral from 0 to pi over 2 of the cosine of theta sine of theta d sine theta, or sorry, d cosine theta. That's an x. And we can compute that differential. Derivative of the cosine is minus the sine, so we get this guy. And hopefully we all know how to solve this one. You could recognize cosine as the derivative of sine. You could do a u substitution if you want, u equals sine theta, whatever. But what you'll find is that this is equal to minus 1/3. Okay. All right, so let's move on. We're going to see this again in a moment. Let me tell you about boundaries of domains now. So a domain, let's call it D, has piecewise smooth boundary. So it possesses the property that this sounds like, right? When you take the boundary of this thing, so maybe it's something like this. The boundary would just be this, curve that I drew. Well, you can always decompose it into a finite number of smooth curves, meeting only at endpoints. So maybe it looks more like maybe it'll look something like that instead. What matters is that at each of these individual components of the boundary, we have smoothness. And again, smoothness, all we really want to assume is continuous differentiability, but it's a lot easier to say the word smooth. So let's go with that. And there's no harm in over assuming. I need to tell you about orientation here. So we choose the orientation. So you notice that I could have drawn the arrow this way, or I could have drawn it in the opposite direction. What we're going to ask is that when we traverse the curve in the positive direction, right? So as if I have this parameterization, as I go from A to B, as I travel in that direction, what I want is for D to be on the left side of the curve. Okay, so if this were A and this were B here, the curve is going this way, and so I want D to be on the left side of the curve, and so it's over here. So that's a choice we have. I've never seen anybody make the opposite choice, so we're gonna go with this one. All right. So let's go back to this example. And this time we're going to integrate over the boundary of a domain where the domain is the quarter disk in the first quadrant. So let me draw it. Here's my quarter circle. There's my 1, 0, 0, 1. And then here is D. Well, then the boundary of D is, yes, it's this curve that we called gamma before, but it's also this guy, and this guy. Right? So it's the union of all three of these curves. Well, we can integrate this pretty easily. This is the integral over gamma plus the integral over, let me give this a name. Actually, let me write it like this. This will be the integral from 0, 1 to 0, 0. And we'll just understand that what I mean is this straight line here. Plus the integral from 0, 0 to 1, 0, xy dx. And so same thing, what we mean by this notation is the straight line between these 2 points. Okay, well, we already computed this guy. This was minus a third. And what's this guy? Well, along this line, we can parameterize it so that, well, the x is 0. Okay. But if x is 0, well, then this integrand is 0, and so this thing should be 0. And then along this horizontal line, well, y is 0, right? We can parameterize it that way, and we'll find again that this guy is 0. And so in total, this integral is again equal to minus 1/3. All right, so let me tell you about a nice theorem that we can use to compute these integrals. It's called Green's theorem. Okay, so let D be a bounded domain. And the plane, R2 or C, right? Let's just say C. I don't think we'll see any contradictions here. Whose boundary consists of a finite number of disjoint, piecewise, smooth, closed curves. Do I want to say closed here? No. I mean, we want the union of all of these to be closed in order for this to be a boundary, but we don't want each individual piece to be closed. I think that's maybe a typo in the book. Let P and Q be continuously differentiable on D union its boundary. Then the following is true. If we integrate over the boundary of D, this differential, then this is equivalent to the double integral over the domain of the partial derivative of Q with respect to X minus the partial derivative of P with respect to Y. Okay, so I won't prove this. This is something you see in your third calculus course when you do multivariable calculus. But I will give you the engineer's proof, a proof by example. So let's take the same integral. By Green's theorem, we can write this as the double integral over the domain of x dx dy, right? Because p here is xy and q is 0, right? So we pick up a minus dp dx, or sorry, dp dy, which is x. And then, well, we parameterize again, we get this as minus the integral from 0 to pi over 2, integral from 0 to 1 of r cosine theta, that's what x is. Dx is uh, dx dy is our differential, becomes r dr d theta. And so we compute this integral, and what we'll find is that this is minus 1/3 again. Okay. So there's another theorem that we should be familiar with from calculus, which is the fundamental theorem of calculus. Which tells us that, well, if capital F is an antiderivative for lowercase f, and we need something else, and f is continuous. I think this is too strong, but that's fine. Then the integral from a to b of f of t dt is f of b minus f of a. And there's a second part that tells us that if f is continuous on AB, then capital F, defined as the integral from a to t of f of s ds, where t is between a and b, this guy is an antiderivative for f of t. So what does that mean? It means if we take the derivative of capital F, what we'll get is f of t. Right? And this antiderivative is defined up to an arbitrary constant. So basic calculus, right? Let me give you one more theorem before I tell you this. But I'm going to need a definition before I do that. So what I'm going to tell you is that it's something not in Gamelin, which is that Green's theorem and the fundamental theorem of calculus, and even Stokes' theorem, which involves 3D calculus. I think there are some others. All of these, when you learn the theory of analysis on manifolds or differential geometry or whatever, all of these come from the same theorem, which is the generalized Stokes theorem. And I don't think I have this in my notes today. Maybe I'll try to work out what it should be and write it down, and we can make fun of me later if I get it wrong. But it's worth trying to write down. But first, let me tell you a definition and another theorem, which will also generalize. If h is a continuously differentiable complex valued function, we define the differential of h to be dh equals partial derivative of h with respect to x dx plus partial derivative of h with respect to y dy. Okay, and then p dx plus q dy is called exact if it can be written as the differential of some function. Okay. So let me tell you another theorem. if gamma is a piecewise, oh, I botched that, pi-wise, piecewise smooth curve from A to B, and if H is continuously differentiable on gamma, then the integral over gamma of the differential is just H of B minus H of A. And so this is sort of like the fundamental theorem of calculus, but for line integrals. In fact, I think it does go by that name sometimes. But anyway, here's the proof just because it's so quick. The integral is equivalent to this guy. This is just the definition of the differential. And well, this is equal to, if we parameterize everything, this is equal to the integral from A to B of dh dx dx dt plus integral from A to B dh dy dy dt. So this is that result we did right at the beginning of the lecture, right? We wrote down the definition of a line integral, and then we use the mean value theorem to rewrite it this way. And then this is the integral from A to B of the t derivative of h. And now we can just use the ordinary fundamental theorem of calculus. So this is h which is h of b minus h of a, right? So b and a, that's x of lowercase b comma y of lowercase b, x of lowercase a comma y of lowercase a. And so this completes the proof. Okay. So when the point of this is the differential kind of behaves like a derivative, right? When I integrate a smooth or a differential over a smooth curve, then what I get is, well, it's analog of a antiderivative evaluated at the endpoints of the curve. Okay, so now maybe it's worth mentioning the generalized Stokes theorem. We can almost see it. Here are my notes. We can almost see it from this identity here. What we should have in general is that the integral along the boundary of some domain let's see, some function h. Let's see, something like this. This is worth making sure I get it right. Let's see. Yes, that's right. Okay. So if you have something, an integral of this form, over the boundary, what happens is this boundary kind of gets transferred over to this differential over here, like this. And the fundamental theorem of calculus, the Green's theorem, the Stokes theorem, they're all just special cases of this identity here. If I had more time, I would maybe think about think about proving this, but I'd also have to introduce the theory of like differential forms and stuff. So it maybe not worth doing. But this is cool, and I would read further into it if you're interested. All right, so let's move on. Let's do another example using that last result. So we can compute this integral pretty easily. The way we do it is, first of all, we parameterize gamma and the following. Oh, sorry, no, I have to give you gamma. That's right. So we're just gonna take a portion of the circle again. Like so. All right, and now we're gonna use our previous theorem to compute this integral. So notice that 2xy dx plus x squared plus 2y dy can be written as the differential of a function h, where h is x squared y plus y squared. Right, we can check this. Dh dx is 2xy, that should go here. And then dh dy is x squared plus 2y, which should go here. Okay, so that checks out. Well, then the previous theorem tells us that this integral, let me call it I so I don't have to write it again, I is equal to the function h evaluated at the endpoints. Right? So this is x squared y plus y squared evaluated from 1, 0 to 0, 1. So we plug these in, we get a 1 minus a 0, which is 1. Okay, so not every differential is exact. So not every differential, not everything that looks like p dx plus q dy can be written as the differential of h for some function h. And now what we're going to do is derive some conditions where this does hold. We say this integral is path independent. So notice I didn't write a path here. If the integral is the same for any path from A to B. So maybe I should write this as the integral from A to B, just to clarify that I do fix my endpoints here. So we say that the integral is path independent. If it doesn't matter which path I choose to get from A to B, the integral is still the same. Okay. Here's a lemma. Let P and Q be, so the usual thing, continuous, complex valued, on a domain D, domain D, then the integral from A to B, P dx plus Q dy is path independent if and only if the differential is exact. Okay. So I won't prove this one, mostly because I'm running out of time. Yeah, but again, another result from multidimensional calculus. So this condition that this guy can be written as dh for some function h is equivalent to its integral from a to b being path independent. Okay. So this differential is called closed on D if the partial derivative of P with respect to Y is equal to the partial derivative of Q with respect to X. So by Green's theorem, this is the condition that the integral, so this is the condition that the integral of the differential is equal to 0. And this follows from Green's theorem, which allows us to rewrite this as the double integral of this one minus that one. No, other way. This one minus that one. Okay. Here's another lemma. Exact differentials. So what does that mean? That means differentials which can be written as dh for some h are closed. So this one is a very short proof, so let's go ahead and do that. If p dx plus q dy is dh, so this guy is exact, then dp dx, dp dy is the y derivative of dh dx, right? So remember the definition of the differential is dh dx plus dh dy dy, which is equal to d by dx dh dy, which is equal to dq dx. And that is exactly what we wanted to show. Okay. So here's another note. Not all closed differentials are exact. So the converse of this lemma is not true in general. However, it is true on star-shaped domains. So these star-shaped domains are about to come up a few times. So I should explain. A star-shaped domain is a domain where, so star-shaped, what this means is there is a point x0 in the domain such that there is a line segment between x0 and x contained in D for all other x in D. So there exists a point in my domain such that when I look around, I can see every other point in the domain. Right? So it's called star shape because that's just a quintessential example. Here's a star, a very bad one, but if I look from, let's say, this point, here's my x0, and I look at any other x, well, I can see it, right? I can draw a line that goes directly to it. It's in my line of sight. And the same holds true for any other point in this domain. But another domain that's star-shaped technically is a disk, right? or a rectangle for that matter. Okay, so a little bit of a misnomer, but that's okay. Okay, so here's another theorem. So we're mostly collecting results that we're going to use in the future today. Let P and Q be continuously differentiable, complex valued, blah, 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 on domain D. And suppose that the following two conditions hold. D is star-shaped. And the differential is closed. Then the differential is exact, which we learned is equivalent to path independence. So this is basically what I was just talking about with the star-shaped domains. So in summary, what we have in general is that path independence is equivalent to exactness, which implies closedness. And then for star-shaped domains, what we have is path independence is equivalent to exactness, which is equivalent to being closed. Okay. So I have just a little more I want to do today that involves this star-shaped domain stuff, but also our friends, the harmonic functions. So I was going to save this for next time, but let's go ahead and talk about it since we're here. So if we have some function u, which is harmonic, then the differential minus du dy dx plus du dx dy is closed. Here's the proof. Let p be minus du dy and q be du dx. Then dp dy is minus d2u dy. So second derivative of u with respect to y. And this is equal to the second derivative of u with respect to x because u is harmonic. So it satisfies Laplace's equation. And so this is equal to the derivative of q with respect to x. And this condition is exactly closedness. Okay. So harmonic function defines a differential which is closed. So now if u is harmonic on a star-shaped domain, then we have a smooth function v. So if u is harmonic on a star-shaped domain D, then we have a smooth function such that dv is minus du dy dx plus du dx dy. Why? Because, well, this lemma tells us that if u is harmonic, then it's closed, or this differential is closed, right? But if we're in a star-shaped domain, then closedness is equivalent to exactness, which implies that there's a function v. Well, it's by definition, what this means is that there's a function v such that this differential is the differential of v. Okay. So what is this equivalent to? Well, if we write out the differential of v, what we find is that this is dv dx dx plus dv dy dy. And so this is equivalent to the conditions and we recognize these as the Cauchy-Riemann equations. Which we derived when we talked about analytic functions or introduced them. Okay. So this tells us that u plus iv is analytic. And so we've derived the following theorem. Any harmonic function u on a star-shaped domain D has a harmonic conjugate on D. Okay, I think I'll go ahead and leave it there today. Any questions?
So harmonic conjugate means that u and v are the real and imaginary part of an analytic function, right?
Yes. Yeah.
Okay.
All right. Let me stop.